Okay, now I will start recording. Okay, perfect. So since I don't know how many of you were here yesterday, so there's no need to repeat so much, right? Okay, just to recap, just for some of you that were not here during the Q&A, because I take advantage of that. So last time we talked about coupling direct fermion to the U1 background gauge field, and we look at the U1A axial rotation, okay? As I wrote it here. And we discovered that the measure of the inner path integral was not invariant under U1A rotation. And it picked up this phase, okay? And this means that the current, the axial current is not conserved, okay? Just to make one thing, this is a crucial comment. I don't know. Some of you who are connoisseur in the covariant derivative would complain that where is the coupling? Did you? Did you notice that I didn't write a coupling here? There should be a coupling G or E or this kind of thing. And even worse, yesterday I talked about the kinetic term, which looked like this one. This is just to clarify that there are two conventions in this business. So 1 over E square, this is a kinetic term, right? Normally in the quantum field theory textbook, you would not see E square here. The reason is I reabsorb E into the my gauge field, okay? If you want, you can restore it back, and then F mu nu has E, right? And F mu nu has another E, then you remove E square. This is by absorption, E to the A, okay? And if you restore it, you would have E in the front. Is that clear? This is my convention. Also in the anomaly here, in the ABJ anomaly equation, if you put restore E in that convention, you would have E square here. Can you see that? Is that confusing? Okay. So there are two conventions. I absorb E into my gauge field. Okay. So that just to make clear. So okay, this is just to be clear. Okay. So now let's see. We can continue from this. So if you want the derivation, and those of you who were not here yesterday, we are at page 17. Notice I designed it to be readable. Okay, it should be self-contained, and the recorded video was already out, so you can watch it if you were not here. Okay, so what I'm doing today is that I would like to show that there is no further quantum correction to the ABJ anomaly. Okay, suppose that we pretend that we restore this E square here. You would say that, is there a higher order correction in coupling, right? Is this an exact formula? Can there is non-perturbative correction, there is further correction in coupling. The reason is, what I would like to show is that there's no further correction to this. This is exact. Okay, so the argument is that you can put the theory on the 4 manifold, which is time times M3. M3 is a closed manifold, okay? Manifold, okay. And what happened is that you can integrate this equation on both sides. So you have integral M4 of d4x d mu j mu a, and you can use Stokes theorem, right, to write it as, okay, I will write it like this: QA at t equal to plus infinity minus QA at t equal to minus infinity, where my QA is defined to be this guy. J0 A. Okay, you agree? Okay, what is this? This is charge, right? And what is this current? This is axial current, right? You agree? This is called the axial charge. So what's the meaning of the left-hand side after I integrate over my four manifold? It means that you compute the charge of the axial symmetry at infinity, and you subtract it at minus infinity. And charge has to be quantized, right? So this quantity is an integer. Does it look surprising for you? So what is an axial charge? You compute the left-handed minus the right-handed, right? So this is the left-handed quanta minus right-handed quanta. This is the interpretation of axial charge. Okay, so this one is an integer due to quantization of charge. Okay. Now the right-hand side, you have QA at t plus infinity minus QA at t minus infinity. You will see that it's equal to 16 pi square d4x epsilon mu nu rho sigma f mu nu f rho sigma. Okay. Is that clear? So the left-hand side is an integer. The right-hand side is also an integer. So if you want to make this equation change, it changed by an integer, right? And as I said to you, you can even put a coupling E square here if you want. Okay? In this normalization, there's no. And if you want to put E square, there's E square here. Okay? And quantum correction will correct it at high order, right? So basically, what I want to show is that you see that the left-hand side is an integer, and this thing is a quantized. So quantum correction don't normally change you in a quantized number, right? It changed by some proportion of the coupling at high and high order. Okay, so, and in fact, I can show that on the left. I will show you in a second. The right-hand side is actually a topological invariant with a suitable normalization 1/16 square. So you can ask me, what do you mean by topological invariant? It means that it can change only when you change topology of the gauge field. Okay, so meaning that what is topology of the gauge field? You have seen example like winding, right? So you can let the gauge field, for example, wind around the closed manifold or this kind of thing. And when you change this topology, the right-hand side can change, and it changed by integer. Okay? So, and also, it's very important that you have to normalize this integral by 1/16 pi square and nothing else. And this will be integer. You have seen that, right? So meaning that the coefficient 1/16 square cannot be shifted even slightly by quantum fluctuation. Because if you change this coefficient, it will no longer be an integer like the left-hand side. Is this clear? So what I'm trying to show you, I used two things. I used to show that this integral is an integer, and this is a topological quantity, okay? And this is solid. In fact, it has a name. This right-hand side is known as Chern-Pontryagin class. Pontryagin class. Some people call it Chern number, and if you good at the classical solution, this is also called instanton, right? Yes, this is why it's a topological, okay? And or even Pontryagin index, this is the same synonym of the quantity on the right. A quantity on the right, I will show soon that it even have a deeper meaning, okay? So are you okay with that? This is the end of the argument. So suppose you put e square here. There's no e to the 4, there's no e to the 6. Okay, it's stopped here. Okay. Yes, please. No, it's very solid here. It's okay. So if you put e to the 4, e to the 6, it will appear in the coefficient here, right? Yeah. So yeah, that's the point. It will no longer be integer. Mhm. So the integer and the proper topological property is very solid here. Please. Yes. It's computed at infinity equal to infinity. It well, it suffer from anomaly, yes, but it's not a concern. But it's still if you compute the charge, it's still quantized. Yeah, right. I will show you further that the right hand side actually has an integer interpretation soon. Okay. Yeah. So you might ask, okay, what's the interpretation of this charge quantization? I already anticipated a little bit. That is, you compute the quanta of the difference between left-handed quanta and the right-handed quanta, right? And now I will show it here. Okay, please. E- It's like okay, it's higher in a coupling basically, higher order in coupling. You will have a e to the okay. Let's put e here. Okay, there will be e square. There will be 2 e to the 4. You have to put some. Okay, good. So I haven't told you, but you probably know from your quantum field theory course. Equivalent way of this is to do it from the triangle diagram. And you probably told also in your quantum field theory course is exactly one loop. One loop result reproduce the result that I wrote here. Okay? You might ask, what about 2 loop? What about 3 loop? Why do we need that? And I said, you don't even need to compute it. Topology told you that it stopped at 1 loop. Please. Ah, you mean a product? Yes, yes. Instanton can factorize, yes, in that case, exactly. Any more question? If not, I will show that this really, I will give now the precise interpretation, what it means, okay? It's a difference of a zero mode. I will show you. This right-hand side is very famous, actually. It's part of the so-called the Artia Singer index theorem. So this is a theorem, okay? So this result is related to this theorem, okay? And bear with me, you will see it, okay. Okay, in Euclidean space, gamma mu's are Hermitian. This also implies that ID slash, which I define as ID minus the Dirac operator, A mu, gamma mu, is Hermitian. Okay? And therefore, ID slash has real eigenvalue. Okay? So we start from here. So meaning that if I write this equation, which you have kind of seen this yesterday, this lambda has to be real. Okay? Okay, now I will show that if this is a non-zero, it comes in pair. Okay? So let me write it down. Given an eigenfunction phi of x with the label n of id slash with eigenvalue lambda n not equal to 0, meaning that I talk about eigenfunction with non-zero eigenvalue. There is another eigenfunction phi n minus with eigenvalue lambda n minus equal to minus lambda given by phi n equal to gamma 5 phi n. You might ask why this statement is true. Okay, let me state it. It's very easy to show. Okay, let me show this briefly. You just use anti-commutation relation between. So this can be shown like this. So this just follow from the fact when you have gamma mu is anti-commute with gamma 5. Okay, so ID slash gamma 5 phi n, you move gamma 5 here, right? And you get a minus sign. Minus lambda n gamma 5 phi n. Okay, you see? So if it's 0, I cannot use this argument. But if it's non-zero, this is true. Okay? So non-zero, the eigenfunction of non-zero eigenvalues always come in pair. This is very important. We have to use this, okay? Right. Since lambda n and lambda n minus was just minus lambda n, okay? Are different eigenvalue. The corresponding eigenfunction are orthogonal. What I mean is that if you compute d for x, phi n of dagger of x, and you compute the one with the gamma 5, okay, phi n of x, this is another one, right? This has to be 0. Okay? Was it clear? Good. And okay, now let me remove this bracket. It's the same. Okay. Now I have to recall from yesterday, we derived this expression. This derived by regularization. How many of you remember this? We did it yesterday. Remember? Okay. If not, you can look at it in the note because this is quite long to derive without doing regularize again. So I'm not doing it again. Okay. It's equation 3.26 in my note. So, okay. So this one is 0 whenever they belong to the, it's not totally 0, right? When you sum over this. Which contribution that received here? That can, the 0 eigenvalues, right? The 0 eigenvalues, you know it has a name. Eigenfunction that belong to 0 eigenvalues has a very special name. It's called fermionic zero mode. Have you heard of this? Yes, this is the definition of zero mode. Okay? Okay. Uh, okay, so let me label this by dagger. Okay, so dagger, therefore, receive the contribution only from the eigenfunction with lambda n equal to 0. These are called zero modes. Okay? Okay. Now, since this is equal to what? 0 here, right? They are simultaneous eigenfunction, which I will call phi u and phi v, okay, of I said I with eigenvalue 0 and of gamma 5 with eigenvalues plus or minus 1. So there are simultaneous eigenfunction u and v, okay, of id slash of the Dirac operator and of gamma 5 For gamma, for the Dirac operator, they have eigenvalue 0, but u and v have eigenvalues plus or minus 1. Okay, so let me write an equation. What I mean here is that if you put id slash, you hit it with u, you always get 0. The same for v. But if you hit it with gamma 5, you get plus 1 phi u. Okay, let's put it like this. And for v, you get minus 1 or minus phi v. Is that clear? So now we are ready to compute this thing. So again, we use this dagger. One over minus 22 pi square d for x rho sigma. So you can sum over n. This is for x, phi n dagger, gamma phi, phi n. You split it into the set of u, phi n dagger, x, labeled by u now, and minus phi v, a dagger of v of x. You agree? Because it's plus and minus 1. This, I can call it n plus, and this, I can call it n minus. So what is n plus and n minus? So n plus and n minus equal to the number of zero mode of the Dirac operator with gamma 5 eigenvalue plus or minus 1. Is that clear? So this has a name. This is called the index of the Dirac operator. Okay? So what I have shown is that the left-hand side is really an integer. It's a difference of the zero mode. Okay? So did this answer your question, a previous question, that why this is related to station? Okay? So this is the famous Atiyah-Singer index theorem. They show that this integral is the difference between the zero mode, the gamma 5 with eigenvalue plus and the minus. Okay? Hmm? Yeah, they normalize with 1 over 32 pi, indeed. Yeah, yeah. Yes, exactly. This coefficient is really important. Otherwise, if you move it around, it's no longer integer. Yeah. So this normal, yeah. Any question? Please. It's just twice, but it's still an integer. Yeah. Oh, okay. So first of all, this can change. So what can change here? So if you change topology, what happened? The zero mode was is not generally not pair, but you can move away the non-zero mode in pairs. So non-zero mode can just disappear or comes in pair. Is that clear? So this quantity remain constant. So when you change topology, you can change only this number. Okay? That's the whole point. of this being topological quantity. Because gamma 5 square to 1. Okay, so what's wrong? Yeah. Ah, yeah, okay. I missed the integral. Sorry, yes. Yep. Yes. Can change. The difference, yeah, but yeah. Yep. So it can change, but to such that these are still remain integer. It can change by integral quantity. If you increase winding number, what is not changed is the non-zero mode. The non-zero mode will go out in pair or come in pair. They are paired. The non-zero mode. The zero mode can change. This number can change. Because these are, look at the interpretation here. So basically, these are this type of eigenvalues, right? Yeah, they can change. Nothing constrain you when you change topology. But it can change by integer. What is constrained is that the non-zero mode will change in pairs. By topological quantity, topological means these guys, when you change topology of the gauge field inside the F, this can change by integer. Okay, yes, think about it. So, yes, please. You can put d mu j, d mu, this one, in the correlation function. Yes. So indeed, you can put this in correlation function. Not necessary. It is what it is. It is an instanton number. Why you have to put it in correlation function? You can define by itself. This is a topological quantity. It can live by itself. You don't need to put in correlation function. Uh, um, I wouldn't call it classical statement because, well, okay. Classical in which sense? In the sense that it's the d mu j5 mu is classical? I wouldn't say so. It has a one loop effect, right? Do you call one loop effect classical? I wouldn't call it classical. Okay, yes. This I agree, yes. Okay. But it's a so okay, fine. This is I don't know how to this is a topological quantity, yes. Yeah, I don't know. I'm just saying that you mean if you say that this quantity alone is equal to this is a mathematical statement. It's a theorem, it's not a good advice, okay? Yes, it is a theorem. What I'm showing you, I'm showing from the property of the Dirac operator. You call this, it's mathematics. It's you can call it classical. Yes, I haven't put any H bar or quantized anything. It's a mathematical theorem. But that's quantum. I'm sorry, it has a coupling. And it's come from one loop effect. Yes, ask in Q&A. Yes, please. Oh, how is it with manifold with boundary? This could change. Yes, you have to. Okay, I haven't. It can receive some contribution from the boundary. Yes, from the zero mode that might come from the boundary. They might enter here. Yes, I'm not assuming that. Right. Please. Winding as an example. So take, for example, this on phosphere. Okay? So you can have a non-trivial configuration of the gauge field. This is like instanton. When you change instanton number, of course, this will change by an integer. That's what I mean by topological. Sorry, yes, now I understand confusion. Suppose you change gauge field by infinitesimal transformation, this quantity will not change. This is what we mean by topological. Is that clear? So infinitesimal transformation in the gauge transformation will not change this. So it's not invariant to the topological change, but it's like it's invariant in a topological sense. Exactly. Only large gauge transformation will make this change. Small gauge transformation that can be continuously deformed to identity will not affect this quantity. That's what I mean by topological. Am I clear? Okay, yes, if you like, yes, this has something to do with the homotopic group, the pi 4 of the pi 3 of S, the yeah, of that. Mhm. No, we're talking about topology of gauge field, not topology of space-time. Okay? Gauge field can wind around space-time. This is the homotopy, right? It's like instanton that I talk about. You remember this function Q? Yeah. More questions? You're welcome to ask me more in the Q&A. But let me conclude. Anomaly is a quantum effect. It's not classical effect. Classically, this J mu A is conserved because it's symmetry of Lagrangian. By Noether theorem, it is conserved classically. When you compute, I change the path integral. Okay, it's path integral. You can do it by one loop diagram, and it's one loop exact. That's what I'm saying. And I'm saying that this is topological in the sense that you cannot change it by infinitesimal gauge transformation. They will not change this quantity. Is that clear? Okay. Okay. Let me move on to the next one. So far, what have we done? So we have done abelian. You remember my A is the U1 gauge field, okay? So you could have asked, okay, what about if I couple non-abelian gauge field to the theory? What would change? Okay, we can do that. And I will demonstrate how to do that. So generalization to non-abelian. gauge field. Okay. Take a mu to be a gauge field of a general group G with generator TA with a B. This will be my gauge indices run from 1 to dimension of G. If G is SUN, this will run from 1 to n squared minus 1. Okay? Okay, suppose that we have a collection of massless Dirac fermion psi I, and we assign the left-handed field to a representation R. Ooh, let me tell you, I don't know how to do boldface in my writing, so I will put something like this. Was it clear for you? This is a denote representation. I will not be so consistent, so apologize. Of G and take the right-handed to be invariant of G. This way, G can be non-abelian, and you can find that there is still ABJ anomaly, okay? And I will show you that if you couple the left-handed and the right-handed differently, anomaly is always non-trivial, okay? Well, unless there's some accident, like in standard model, that some anomaly was cancelled. But I will show you this slowly, okay? At the moment, we're talking about ABJ. We're not going to gauge anomaly yet, okay? Everything is a background field for now. Okay, so if you write Lagrangian, you will see that you have to split this into this part minus I sigma d I, okay? I gamma mu d mu minus I a mu a t of r a 1 minus gamma 5 over 2 psi. Okay, this is how you write in the chiral basis, and this is how you write in Dirac basis. Okay, here d mu is now look like this, a ta of r, and ta of r is just the generator of the representation r. Okay, is that clear? This is how you do it. Okay, so now you also have axial current, which now look like J mu A equal to psi bar gamma mu 1 minus gamma 5 over 2 Ta of R psi. This is how you write down the axial current. This axial current look very similar. If you put in U1, you will see that we recover our previous result. Okay. So now the ABJ anomaly will become d mu j mu a equal to 1 over 32 pi square. You might say, why I'm keep changing from 16 to 32? If you stare at it carefully, this is a very subtle point I will explain, okay? It comes from some group theory factor. Mu nu rho sigma, F mu nu, F rho sigma, then it contain, okay, this has to have index A, B, C, and it has an extra contraction, A, B, C of R, okay? This D has a name. It's a group theory thing. It's called anomaly coefficient. It is defined as follows. DABC of R is the trace of TA in the representation R, TB in the representation R, and TC in the representation R. Close bracket. Can you see this clearly? Oh, can you still see it? Especially those at the back. Yeah. Okay. So what's the property of DABC? They are totally symmetric, right? You can permute them in the trace, and it's subject to anti-commutation relation. You agree? How many of you have seen this DABC? Oh, so okay. Good. So this DABC, if you wanted in the okay. So if you want, okay, this can come from the triangle diagram of this type, okay? So let me draw it. So what happened is that the triangle diagram, if you do computation of the Hooft anomaly, of the ABJ anomaly, you would put a mu here, a sigma here, well, with some color, a C or a B, and then you put a J here. Okay? And you swap these two legs. So this become a sigma C, a mu B, and then the same as J. Okay? Some of these two diagrams will keep the right hand side there. Say again? Yes, it's contracted, right? BC with DABC. Sorry, it's a multiplication. Yeah, sorry about that. Okay. So this is the triangle diagram that you would compute to get this result. And you can generalize it even more. So suppose that you have left-handed and right-handed fermion. In representation RL and RR of G, what you do, you will have J mu A psi bar gamma mu 1 minus gamma 5 over 2 TA of RL psi plus psi bar gamma mu 1 plus gamma 5 over 2 T right A of psi. Okay? And then the ABJ anomaly will just look like d mu J mu A 1 over 32 pi square epsilon mu nu rho sigma f b mu nu f c rho sigma. And then you multiply it by DABC of the thing on the left and minus DABC of the thing on the right. Okay? So left-handed and right-handed tend to cancel each other. Okay? This is the signature of the ABJ anomaly of this type. Now, let me mention. Okay, so there was also some trick which is used quite often, that instead, if you have both left-handed and right-handed field in your theory, what you can do instead is that you can look at the antiparticle of the right-handed guy, which will become left-handed, right? And collect them and consider only left-handed. Am I clear? This is another point of view you can do. It gives the same result because of this minus sign, okay? Excellent. Now, last thing I would like to mention is called gauge anomaly cancellation. So far, we have considered a general current, J A mu A, right? Axial was just one symmetry that you can consider. You can consider other symmetry like vector, you will get zero. But you can put any global symmetry here. Importantly, you have two gauge fields here, and you put whatever current to your global symmetry as a dot, right? So you can change this. But you can take the J to be the current that coupled to the A gauge field itself. Meaning that now J is a gauge current. Okay? Can you follow? Once you do that, ABJ anomaly turn into something called gauge anomaly. Okay, let me write it. So I know that you got confused between dynamical and background. I received some question like that, but this is a fully, okay, let me write it. So when this current is itself coupled to the dynamical, let me emphasize now it's dynamical gauge field, A mu A of G, gauge invariant, requires that the anomaly must be absent. This means that DABC has to be 0. Is it clear? So far we talk about JA being a current of some random global symmetry in the theory. You can take to be any, but you can take it to be the gauge field itself. So the diagram now, change it to be like this. If you have to compute this, it has to go. Otherwise, your theory is inconsistent. Okay? That's a statement of the gauge anomaly. Okay. So let me state one thing. So any consistent quantum field theory must be gauge anomaly free. This is you probably heard of this, right? And this is the derivation. So you see my principle of doing this lecture. I start from global symmetry, and I ask myself if you can gauge it. And if possible, we gauge it, and we look the condition that allow us to gauge that symmetry. Okay, please. Okay, very good. So as I said, if you have right-handed, you can turn it into the left-handed with antiparticle. Okay, and then you sum. That has to go. That has to vanish. Okay, that can be a point of view, a convenient point of view. Yeah. So let me state without proof because I don't think I have time, but you can read it in my note. I would like to do one example, really. I mean, just to show you, because this can be quite important. I know it's quite basic. Now we are back into the vintage era again when people knows this. So if the representation R is real or pseudo-real, then DABC of R is 0. So one way to cancel this anomaly is to put things in its real or pseudo-real representation. So I will not prove there. You can read it in the note. Okay. So can you give me example of pseudo-real representation? Take SU2. What is pseudo-real representation? The fundamental representation. You define in the note. You have you seen this thing or not? Who know what is pseudo-real and real representation is? Oh, okay. Then let me do it. Okay. So real or pseudo-real? Okay, you know that, for example, if we are in a complex, okay, let's start with a complex representation. Fundamental representation of SU3, you see that it have a 3, and then there is a 3 bar. This you know. Okay, this is known as complex representation. Representation that the complex conjugate and itself are the same. This is belong to the class that we call real or pseudo-real. Okay, so let me do it. The representation R is equivalent to its complex conjugate if there is a similarity transformation ITA of R. This is what you mean by conjugate of the representation. Is it clear? So when I take, this is a generator of the complex conjugate representation. Okay? And if it can be related by this guy to this one, this is similarity transformation, right? This means that this representation is either real or pseudo-real. Okay, so representation is equivalent to its complex conjugate. First of all, is it clear? I will give you more criteria later. Okay, so this means that you, okay, depend on convention. I use a physics convention where the T is a Hermitian. Okay, so this means that I can do things like this with a transpose that equal to S T R A S inverse. Okay, good. This, if this is satisfied, if this holds, R is either real or pseudo-real. This is a condition. What I mean by real and pseudo-real is this condition. Okay, next. It is real. R is real if, in addition, there is a similarity transformation T tilde A of R equal to, I'm sorry, there's too many R. This is a matrix such that TA tilde of R is imaginary and antisymmetric. If this can be done, you call this representation real. Okay? If this is impossible, you call it pseudo-real. Okay, these criteria involving you writing down the T explicitly and look for the transformation of this type. Okay, there is an easy table you can look at, which is by now is familiar. It's called Yamatsu, Encyclopedia of Group Theory. You look at the representation, and then this R or PR. R stands for real, and P is pseudo-real. But for your basic, you should know example. A joint representation of SUN is always real. Okay? SU2, fundamental representation of SU2 is pseudo-real. Fundamental representation of USP2N, you have heard in some Gong show, that is pseudo-real. Okay? So these are representations that you kind of know. Okay? And now to prove that D is 0, you just have to use the trace. Okay. So since we are here, let me. In either case, trace of TR, A, TBR, TCR, this is our D, right? Okay, what happened? You can use, I erase it. You remember this equation? TR of A equal to transpose. You remember this equation? Plug it in, please. You will have minus, because there are 3 of them, right? So you have a minus sign, and S will cancel among them upon the trace. So you would write it like this. Where I have used that trace of transpose is a trace of itself, okay? And what does it mean? It means that it's 0, right? Okay. Are you convinced? Okay, perfect. So, okay, how many of you have seen this? Okay, good. Then I think I should do standard model. Yeah, because this is important. Whenever, okay, last one before we take a break. We will take 5-minute break, okay? Last one. So whenever you have a doublet, you know that standard model always come with the fundamental representative of SU2. Whenever you hit it with this trace, forget about it, it's zero. That's a benefit of this thing. And you can construct a very simple theory which is anomaly free by using this technique, right? So yeah, vector matter and this kind of thing will not have anomaly. So we will study consequence of this after the break, okay? Let's take a 5 minutes break. So, okay, just to tell you, what I'm telling you here is back to the vintage era again of anomaly. So this is a very well-known part. Some of you might have read it in books somewhere, okay? Now, okay, we explore the consequences of this thing that I just showed you, that the DABC vanishes for whenever the representation is real or pseudo-real, okay? So consequences is that no gauge anomaly for the following group: SO2n plus 1, SO4n with n greater than or equal to 2, USP2n for n greater than or equal to 3, G2, F4, E7, and E8. Okay, so you might say why we need this group, they exist. So, okay. Moreover, even if E6 and SO4n plus 2 with n greater than or equal to 2 have representation that are neither real nor pseudo-real. Pseudo-real, okay. For example, E6 can have complex representation. DABC still vanishes. So you can forget about this group, okay? So what is left in your table? SUN and U1. So anomalies are thus possible only for gauge algebra that includes SUN and U1. Okay, this is an important statement. Okay, since we come this far, we should do this computation once in our life. As I said, there's a once in our life always in the education that you need to pass through once, is to show the gauge anomaly cancellation in the standard model. Why I'm choosing this thing? Because standard model gauge group is gauge algebra is SU3 times SU2 times U1. So you have to learn how to compute this thing in when the group is factorized, okay? I will do this. And this is beneficial for you because this is from a basis when you, how many of you still work on supersymmetry? I should turn this recording off, it's very dangerous what I'm going to say. It's vintage stuff. So as you know that one of the, how many of you know Seiberg duality? Seiberg duality. Wow. Okay, I'm not continuing. Anomaly matching. So the following computation you can apply not even for the gauge anomaly, but for various Hooft anomaly. As you say, you just say, okay, the following statement is that I'm doing this for dynamical gauge field. But in principle, all the thing can be applied for when you have background gauge field, right? Now you in my lesson you see that I always start with the background field and I gauge it. Here it's the same technique. So what I'm telling you now, it can be also useful for other computation. Okay, so let's do this thing together. Okay, we consider gauge algebra to be G equal to SU3 times SU2 times U1. Okay. Okay, and now I will take the interpretation that I introduced to you. I will collect all left-handed fermion and antifermion fields. We will consider only first generation. Together. Okay? So let me collect it for you. Let's start with the left-handed one. So up and down quark on the left is in 3, 2, and plus 1. Okay, let's look at this notation. Since there are factors, I have to tell you what is in SU3, what is in SU2, and what is in U1. Okay? This is 3 fundamental representation of SU3. This is fundamental of SU2, and this is carries plus 1 charge. Okay? I will normalize the U1 charge so that it's an integer. In textbook or in a standard way, you divide everything by -1/6, okay, by -6, okay? Okay, now you have neutrino, electron, and then this is in 1, 2, and charge -3. And now the right-handed guy, I will put a star, meaning I look at the antifermion field, okay? So, for example, this one is in 3 bar, 1 -4, dr star. Or if you want to take a star off, you just conjugate everything. So it will be 3, 1, plus 4. Is that clear? Okay, so I put a star because I will compute it as if it were belong to, I collect everything in the left-handed. This is a convenient notation, okay? 3 bar, 1, plus 2, and electron right is 1, 1, plus 6. Okay. Okay, 1. I'm sorry about underline. I'm not good at it, but you know what I mean. Okay. Excellent. Okay, now this is the important part. So now you said, how do you compute a DABC? Yes, you have to do it brute forcely. This is true because, well, there are 3 factors. So you have to run all the indices in A, B, and C in all possible factors. Okay, can you see that? And when it's U1, you just replace this by charge. Okay, that's a thing. However, if they belong to different group, this thing become factorized. This trace that you see here get factorized. So you just compute this group separately. Okay, but the trick is that in computing DABC, since it has a trace, we only need to consider the combination of generators of G being that for which the product TATB of TATBTC is neutral under G. Why? Because at the end of the day, you take a trace, right? DABC is defined by that trace. Because if you take a trace and there is no neutral guys left, what you get? 0. Because generator is traceless. Remember this, right? Is it clear for you? This statement. This is very important. It will reduce the work by a lot of amount, okay? So this is because due to the trace. And DABC vanishes for the others. Okay? Is that clear for you? This is a very important statement. Indeed, this when you compute any Hooft anomaly, it works in the same way. This is gauge anomaly, but Hooft anomaly also works in the same way. If the product of the generator is not neutral under gauge and the group that you want, forget about it, because at the end of the day, you take a trace, it will go. So we can make invariant out of either 0, 2, and 3 SU3 generator. This is why, since if you take adjoint representation, why you in adjoint? Because you are using generator, right? Generator is in adjoint representation. This and this contain singlet. Okay. You can also consider 2, 0, 2, or 3 SU2 generators. And any number of U1. Okay. So what I mean here, if you find this a bit abstract, look at this example carefully. Okay. So please look at this table, and I will start doing this thing carefully in front of you. Okay. So let's start from this one. So there are 3 generators you have to look, right? So let's look at the first one. SU3, SU3, SU3. This notation means I look at generator from SU3, SU3, and SU3. Okay? So what happened? Look at the table. You have 3 plus 3 bar plus 3. Okay. Look at this. 3 plus 3, right? Plus 3 bar. Let me see. Did I? Yes, because U and D, right? U and D contribute 3 and 3. 3 bar plus 3 bar plus 1 plus 1 plus 1. These are the representation that you see, only for SU3, right? What's the property of this? If you conjugate this, you get this. And these are self-conjugate. So these are real representation. This means that ADABC equal to 0 for this guy. Okay? If it's not 0, I think we will be in deep trouble. Standard model has a gauge anomaly. This is not, not something that we want, okay? This is the first one. So you see, we have to use this fact, okay? Now let's look at the second one, SU3, SU3, U1. The anomaly is proportional to. What do? You sum over anything that is transformed under 3 and 3 bar because of this, okay? And then you sum over U1 charges. Is it clear for you? Because you put one generator being the charge now, it's a U1, right? So what do you get here? Let's do it together. So you get 1 from U, 1 from D, and then you have another 1, right? Sorry, you put 1, okay, then you have -4, right? Okay, then you have another 3 bar coming from there, then you get +2, right? Miraculously, it's 0. You see the anomaly for U1, it's like a miracle. Who would tell you that this random number sum to 0? It's a surprise, right? If this is not a surprise enough for you, let's do further. Okay, what is this one? Can anyone tell me that I don't even need to compute this? Because of, please, why? SU2 representation is pseudo-real. Forget about it. Yes, so no anomaly. Since SU2 representations are real or pseudo-real. Okay, now SU2, SU2U1. You just use the same trick as before, right? You sum over 2, anything that is in the doublet with the U1 charges. What do you have? Okay, let's look at anything in the doublet. U and D contribute 1 and 1. And then there is another 1, right? And there is a -3. And this is 0. Okay? Last one is the most non-trivial one. This is U1, U1, U1. I can ensure you, if this is 0, you almost ensure that your theory is consistent. Because this would involve sum over U1 charges cube. And this would be 6 times 1 cube, 2 times -3 cube, plus 3 minus 4 cube, plus 3, 2 cube, and 6 cube. You have to use calculator a little bit or Mathematica, and you will show that this is really 0. Okay, so our world is consistent. So this is an anomaly. There is another one I have to tell you since we come this far. It's coming from coupling theory to the gravity. By the way, is this clear for you before going further? Please. I don't know. I really don't know. You mean infinite dimensional? Discrete. Not of this type. Okay, let me, good. This I know. So, okay. So, you see that what I rely on is the current. For discrete symmetry, there's no notion of current. To define anomaly of discrete symmetry is a topic of Michele do Sotto. So he will do it in terms of topological defect or this kind of thing. There is, by the way, for abelian group, there is something called background field. I haven't tell you how to couple background field for discrete symmetry. You can do that for Zn. For non-abelian, I don't know. This is current topics of research, okay? So I will leave it to the next course for you, okay? Yes. So, and okay, observe this following. You never mix different group. You never mix different non-abelian factor together. For example, what happens if you do SU3, SU2, U1? Can someone tell me what's going on? You cannot form a singlet, indeed. And when you take a trace, there always generator that is left. And when you take the trace, since T is traceless, it go, it vanishes, okay? It vanishes. So this is why we never consider non-abelian factor in a mixing way. If there's non-abelian factor, you have to consider them together. Am I clear? Okay. Last one is the gravitational U1. So So you can also have a further constraint by coupling theory to gravity. And as you know, gravity act on, yes, please. Yeah. Let me see. Oh, this means that I made a excellent. Thank you that you telling me this. Let me check. 3, 1, 4. No, because look, there are 3 guys there. It's in the triplet. Yes, you have to sum 3 times because it's in the triplet. Yes. Whenever you're not involved in it, you have to sum number of time it happens. Yes. Okay. Yeah? Okay, thank you. So if you couple the theory to gravity, and if you compute the expectation value of the current, you will have a terms like this. So trace of TA, epsilon mu nu rho sigma. This is the curvature. Kappa lambda r kappa lambda rho sigma. Okay, if you couple to the gravity, you can have this term. So can anyone tell me what happened here? If you have abelian factor, you couple to gravity, what happened? Never have to consider, right? Because trace of TA is just 0. But what you have to consider, the U1, right? Because U1, it appears as charge. So you have to consider U1 gravity, gravity. Look at my notation. U1 is here, this is gravity, this is gravity, okay? So you just sum over U1 charges. And indeed, you will see that there's another non-trivial cancellation. This is 0. Okay, so this is the last check for the standard model. Okay, I think I almost run out of time. Can I, yes. I'm putting a background for space-time symmetry. Is a background field. It's working in the level of, yes, exactly, because you're coupling to gravity and you look at the scale below, the gravity scale, yes. Because I want to do quantum field theory. I don't want to do supergravity. Please. Not supergravity, why I said put super? I'm sorry. Yeah, I'm sorry. Yes, I said I don't want to do gravity theory, gravitational theory. I just look at the scale far below gravity, yes. Okay. Any other question? If not, I would like to leave one thing for you. And I think this is very important. This is far from, well, it's also vintage, but it's less vintage than this. So there is another type of, okay, let me summarize. So what have we done so far? So now we look at the anomaly that come from, you know, the Fujikawa method. You have seen that we look at the axial current. Okay, even if the theory is have a axial current, the ABJ anomaly, it doesn't mean that the theory is inconsistent, right? ABJ anomaly was fine. Unless you put that current to be the gauge current, then it has to cancel. Is everyone clear with this? There is a totally difference between ABJ anomaly, it's more general, and then you specify ABJ to be a gauge current, then that has to go. There is another type of anomaly which does not belong to any of this class, and I would feel really guilty for the whole my life if I'm not even mention it. Okay, this is called the Witten anomaly. In 2024, if I lecture a course on anomaly, if I don't mention the name Witten anomaly, I think it's a failure of the lecturer. So let me state, and if we have time, we can go over it this afternoon. If not, I will leave it for you. Okay, but I have to mention something. Witten anomaly is the type of anomaly which is topological in nature. So yesterday, some people come to ask me, is it topological? It's kind of physical or not physical because you have to compactify the time direction and so on. This is purely topological. It cannot be obtained by triangle diagram. Some people call it non-perturbative anomaly. There was also misnomer, which in 2024, well, some people still call it, but I think it's okay. If you know what you're doing. It's called global anomaly, okay? So it's due to Witten. Okay, let me state it. It say that an SU2 gauge theory in 4D with an odd number of wild fermion multiplet in the fundamental representation. Some people call this odd number of Weyl doublet, right? Okay. Is inconsistent. This is the statement of this anomaly. It just killed the theory completely. No debate. Okay? So suppose that you put one left-handed fermion in a doublet of SU2, that the theory, forget about it, is inconsistent. Okay? So if we have time, I will show you that whatever tool we have done for our Fujikawa method can be copied here by taking a square root. Can anyone tell me why? Because 1 Dirac equal to 2 Weyl. So if you look at Weyl fermion, I take a square root. And that square root will lead us to disaster. Because the square root has ambiguity of sign. Clever, huh? So yeah, that sign will make partition function vanish identically when you have odd number of fermion. If we have time this afternoon, I'm happy to tell you about this story. And I think it's really, really interesting. It's really beautiful, actually. So, but if not, okay, I would like to end my official lecture here. Okay, thank you.